I can't hear it. It's coming out? Okay, well, thank you. We have a saying in English, a very old saying, that to err is human, to forgive is divine. We've had to update that in my lifetime. To err is human, to really foul things up requires a computer. So we finally got it going. It took a few minutes. And it's unfortunately cutting into my time, and that's ordinarily not a problem, but I understand that I'm standing between you and lunch, and that's never a good place to be, so I'll try to keep it brief. I've decided this morning to talk about design in astronomy. It's something that we talk about quite a bit in creation circles, and to kind of lay the foundation of why I'm talking about that, there are really two explanations of how we got here, how we in the world got here. And they're not advancing the slide for me. There we go. All right, and for lack of a better word, I'm going to define one of those as evolution. And I'm going to define evolution as a purely natural, purely physical process. Now, an evolutionary biologist would argue with me about this. They'd say, well, evolution is variation in gene pool frequency or descent with modification. But you have to realize that evolution is not just about biology. There are theories of geological evolution, there are theories of astronomical evolution, cosmic evolution, there are theories of evolution of law, history, society. Virtually every area of human endeavor has been touched by evolution today, evolutionary thinking. So to kind of unify all that into one thing, I would define evolution in a very broad sense, and that is a purely natural, purely physical process. That is, there is no creator involved in any of this. And of course, the contrast to that is a creation approach, and that would be, if I want to define it in a very similar way I did evolution, in a very broad way, would be a supernatural process. Now, I want to make it very clear, I'm not talking about just any god or gods or agencies operating. I'm talking about Yahweh, the God of the Bible. Jesus Christ, as we're told in the New Testament, as the creator of the world. And many Christians today, I'm sure it's true here in Norway as well as it is in the United States, they ask the question, well, is it really important what we believe about evolution? After all, or about origins, and how we came to be, because after all, as long as we have Jesus in our hearts, does it really matter? Well, it turns out it does matter, because ideas have consequences. You tell me where you start, you give me your presuppositions, and I can tell you where you will probably end up in your reasoning here. And when it comes to origins, one way I can look at it is to point out that it colors how we look at the world around us. You see, the problem is the creationist sees design and purpose in things. When I look at the world, I see a kind creator who's provided for us. But if you believe in evolution, then you don't see any kind of design, because there is no design, there is no designer. All you see is, in the case of living organisms, chance and struggle, survival of the fittest. In the case of astronomy and other areas, it's just simply chance processes going on. The Earth came about through a long series of chance processes, and here we are today. The universe came about through a chance process, and on and on and on it goes. There is no design, there is no purpose. And there's a reason why this is so stark, because we begin with two very different assumptions. One begins with the assumption of theism, and the other one starts with the assumptions of atheism, or usually atheism. Sometimes we use that term atheist as a pejorative term. When I was growing up, my parents would frequently talk about atheists, and it was always kind of a dirty, nasty term for people. And I've come to learn, well, they're people too. They're just simply misguided and wrong about these things. But I'm very confused with Christians, though, that take an atheistic worldview, even though they believe that Jesus is the Redeemer. Apparently, they don't believe he's the creator, at least not the way I understand it to be. And it's very important, I think, for us to look at these things. And I'm going to illustrate how we can look at things very differently by showing you three photographs. This first one I want to show you is a photograph of a nebula. More specifically, we call it the Horsehead Nebula. That's the name of it. Can you all see the horsehead there? Yeah, it's a very beautiful thing, isn't it? One thing that really attracts people to astronomy is all the pretty pictures that we have in astronomy, more so than any other science, I believe. I just published a book came out in December just for Christmas, called The Heavens a Different View. I've distributed a few copies here for if you want to borrow them from somebody and look at it. But it's got these pretty pictures with some essays I've written in it. I took some of the photographs myself, but some of the other photographs were taken, most of them were taken by two other amateur astronomers who are better astrophotographers than I am. They can take much better pictures of astronomy. I'm getting better at it, but they are really good. I need to learn from these guys so I can improve my techniques. Anyway, this particular photograph was taken by one of those amateur astronomers, and believe it or not. And when you look at it, it's pretty, but when a physicist or an astronomer looks at this, we see something more than just the pretty pictures. That's the second layer that you can look at. What we see is we see a few stars scattered around, and then we see this red coloration across the top that's largely missing along the bottom. Well, what is that? Well, that's what we call H-alpha emission. Some stars you see there in the foreground, those blue stars, are producing ultraviolet radiation that ionizes the hydrogen in a cloud in space. And the electrons pretty quickly want to get back to the protons and form hydrogen atoms again, and as they do, they cascade downward, giving off photons of light. And that red you see is a particular transition between electron going from the third orbit down to the second orbit. You studied that in high school, chemistry or physics, the simple Bohr model. It's a little naive, but from the third to second orbit to get that beautiful light. It's a very distinctive color that every astronomer quickly recognizes. And emission nebulae typically have that red color in them. Many of them do, at least. Now, what about the bottom part of the photograph? Well, you've got this big cloud of gas that's hundreds of light years away from us, and then there's this big bank of dust particles. Dust particles are solid bits of matter, not gas, but solid bits of matter, but very, very tiny little particles, microscopic. And big cloud of it, it's many light years across. It's what it lacks in density, it makes up, more than makes up for in size. And dust particles tend to scatter light and make light dimmer, make the light fainter. And what that big dust cloud has done is it blocks the light of more distant stars. If you look at the top of the photograph where the red is, you see how dense the stars are? When you look below, the density is quite a bit less, isn't it? That's because you're seeing stars that are this side of the dust cloud, but not on the other side. It's totally opaque and blocking our view. That's a common problem in astronomy. We can't see the core of our own galaxy because of all the dust that's in the way. Now, to the lower left, there's a big blue glow, and there's a star there, maybe several stars close together that are just inside of that dust cloud on the near side of it. And they're scattering, the dust particles are scattering light from those hot stars down there. And scattering of light by this way is very dependent upon wavelength. Shorter wavelength, that is, blue light, is scattered a lot more. If you ever see haze in the atmosphere, it looks blue because of that. The blue sky, it's blue because of scattering. It's actually scattering other light of the sun, but blue gets scattered the most. So you have this, when you see what's called a reflection nebula, we know it's from dust particles, you get that blue glow on all of that. So a lot of good physics going on there. By the way, many of my astronomy colleagues tell me that if they ever find the other half of this nebula, they will name it after me. Okay, here we have a picture of a comet. This is comet Hale-Bopp. You all remember that comet back in 1997? It was the brightest comet in my lifetime. It was an amazing comet. People from New York City actually saw that comet. I didn't think it was possible to see a comet in New York City, but it happened in my lifetime. Now, what is a comet? Well, it starts off as a little chunk of ice that's a few kilometers across in some cases. When I say ice, I'm talking about water ice. I'm talking about frozen carbon dioxide. What's frozen carbon dioxide also known as? Dry ice. Is that, you ever handled dry ice? Who's handled dry ice here? How long did you handle it? More than 2 seconds? Probably not. It starts to really burn. Getting you frostbite if you hang on to it. Very cold. Also frozen methane and a few other things that are normally gases that are inside of this. And then mixed inside of that are a bunch of little dust particles. Remember the dust particles I talked about before? Well, we call it a dirty iceberg is what we call the model. It's, by the way, it's awful porous. It's got a lot of openings in it. Its density is far less than normal ice because it's got so many holes in it. And they orbit on very long elliptical orbits around the sun. Here's the sun that comes in like this once every orbit and way back out here and spends most of its time out here very, very far from the sun. So it remains frozen. But once each orbit, a comet comes in close to the sun, and when it does, the heat of the sun warms it up, and it causes the ice is there to sublime. That means it goes directly from the ice phase to gas. It doesn't go through a liquid phase. It goes, dry ice does that normally on the Earth, but even water will do that. It'll go directly from, H2O will go directly from ice to gas if the pressure is low enough, and it is in space. So it suddenly expands outward very rapidly as it turns into a gas, because after all, it's expanding into a very low pressure environment around it. And you get this big big gas cloud, very thin, but still a gas cloud around the nucleus as it orbits around the sun. And sunlight irradiates that gas and causes it to glow and giving off light. Again, it's UV, ultraviolet radiation from the sun doing that. Meanwhile, it knocks off dust particles in the process. And the solar radiation pushes those dust particles away from the sun. And the gas particles, so the gas molecules and atoms, and the ions more often than not, are blown back by the solar wind as well. And that produces the tail. And so you can always tell which direction the sun is because the tails point away from the sun. So you know the sun is off to the left some distance in this photograph. Now down there to the left, you have what's called the coma. That's a big gas cloud around it, and it could be tens of thousands of kilometers across. The nucleus is very tiny. You can't really see it because it's overexposed down there, but it's only a few kilometers across anyway. And we're looking at this from tens of millions of kilometers. And the tail can be hundreds of millions of kilometers long in space. And the dust tail is the bluish tail, I believe, and the ion tail is the white one. I never can keep the two straight, but it's being pushed back by the solar wind and radiation. Quite a bit going on there, again, the physical processes. And then finally, I have the Ring Nebula. This is one of the coolest things to look at through a pretty large telescope. We have an observatory at the Creation Museum. We do public programs, and in summer and early autumn, this is one thing we always look at. We have a big half-meter telescope we use to look at this particular object. And it doesn't quite look this bright or this colorful. You see a little smoke ring-looking thing here. And this is an example of what we call a planetary nebula. Now, it has nothing to do with planets. It's just a misfortune that they started calling them that. They call them that because through the telescopes, they look like a little disk. And a planet looks like a little disk in a planet, and through a telescope as well. So it's kind of a poor choice of terms that we're stuck with it. And for a long time, we thought this thing was like a soap bubble of gas. We now have changed our mind. We've changed it to that we now believe it's more like an hour. You know what an hourglass is? Hourglass, put sand in, it drops down. More of an hourglass. And the shape that you see depends on the orientation. Are you looking at it like this? Or are you looking at it like that? Or somewhere in between? And so we're looking down through the top or bottom of this hourglass, as it were. Now, planetary nebulae always have a little hot, bright star at the middle. You can see it there at the very center. It's a very hot white dwarf star. White dwarf stars are interesting. They're about the size of the Earth, but they can have the mass of the sun. You may have heard about stars that if you took a teaspoon of those and scooped it out and brought it to Earth, it'd weigh as much as an automobile. Those are white dwarfs. They're very interesting stars. And every one of these planetary nebulae happen to have one of these right at the center. I don't think it's a coincidence. And the general idea is that in the past, this gas has been blown off of the star to form this outgoing expansion. You might think, well, it got blown off like an explosion or something. No, it's not nearly as violent as that. It's more like winds blowing things off. That's our understanding, at least, of planetary nebulae today. All right, well, I have to ask the question, what did you see in these three photographs? And I think all of you would agree that you saw some very beautiful things, didn't you? That's one of the cool things about astronomy. We have nice pictures. It's even better when you can see some of these through the telescope. How many of you have ever looked at the planet Saturn through a telescope? Were you impressed? I first saw Saturn through a telescope, a small one that I had growing up. It was over 50 years ago. It was in September of 1969. And I could not believe what I was looking at. It was small, it was faint, but I could clearly see the rings around that. And I was hooked. I've never gotten tired of looking at Saturn. I've never recovered from that experience. And we have some really cool telescopes at the observatory. I have a 127 millimeter refractor, which were made for the planets. And so that's my planetary telescope back home. And the views of Saturn through that thing are incredible. I've been trying to get some good photographs. I've not succeeded yet. I'm doing something wrong. I'm hopefully going to figure that out. But I hope to get good photos. But the views through the telescope are really remarkable. So that's one of the cool things about astronomy. What got me hooked on early on, just the beauty and wonder that you see. Now, I've also shared with you some interesting physical processes. Now, if you're not really into physics, well, you're probably not that impressed with it or didn't really follow it too much. That's okay, not for everybody, but people into physics, that's really cool. What we can figure out, the composition and temperatures and distance, all these cool things we can get by looking at the physics. So everybody sees the first part. A few people see the second part. But there's a third part that many, many, many people miss. Astronomers, professional astronomers, see the first part, they see the second part. But most of them miss the third part. Do you know what it is? What is it? It's God's handiwork. God's handiwork. It goes back to Psalm 19. The heavens declare the glory of God, and the sky above proclaims his handiwork. It's like a large billboard advertising God's existence. However, I think you can misunderstand that message sometimes. Sometimes I'm driving along and I see a billboard, or sometimes I'm watching television and an ad comes up, and I have no idea what they're advertising. That ever happened to you? Yeah, okay. Maybe it has to do with my age. I tell young people I think I was cool once, but that was like a half century ago. And I may have been wrong back then, I don't know. But times have changed. They don't advertise to people my age. They advertise for much younger people. And sometimes I'll be driving along and see this billboard, or I'll see an ad on TV, and I'll turn to my wife and I'll say, "What's that advertising?" And my wife says, "I have no idea." So sometimes it's difficult to kind of gather the message coming across. And I have a whole presentation I do on that. That's not my point today. That's kind of like a rabbit trail at that point. But, Psalm 19 tells us about the heavens declaring God's glory like a billboard or like an advertisement. And Romans 1:19 and 20 talks about that too. It says that men are without excuse because that message is there. Two things that Romans 1:19 and 20 tell us: God exists and he's very powerful. Doesn't tell you anything else, but it tells you that much at least. Well, I have found that design is not a conclusive argument for most people. I see design and I recognize it. I have a hard time defining it, but I think I can recognize it when I see it. And here's the problem with that. If you already believe that there's a creator, then you seem to see that and you're convinced pretty readily. But if you've rejected the idea that there's a creator, then you're probably going to ignore that evidence or just explain it away. And I'll come back to that towards the conclusion of my presentation this morning. So I'm going to just delve into a couple of topics. There are not many. Don't have a lot of time to share with you some interesting things that I've noticed in astronomy. This is a photograph of a total solar eclipse. I took this 5 years ago in 2017. Anybody here been to a total solar eclipse? I have been to 2 of them, and they are the most remarkable things I have ever experienced. When you see a photograph like this, just know one thing. This photograph doesn't really capture it. It really doesn't. It's more beautiful and wondrous than you can imagine. This thing's up in the sky and it looks surreal. It's just amazing. And it's like sunset all around. You can see some brighter stars. And you look around and just see what's happening around you. And the effect it has upon people is amazing. I've been to 2 total solar eclipses. The first time we ran a audio recorder during the thing. And then the last one we had a video recorder going. And I was leading a group the second time, and I was trying to tell them, look for this, look for that. But after just about 20 seconds, something remarkable happened to me, and people who know me will be surprised. You know what it was? I shut up. Yeah. My wife can tell you that almost never happens. The first eclipse, I don't think I said 2 words during the entire thing. I was totally, dumbstruck, which means I can't speak. I mean, I am so focused on what's going on around me that I just have a total loss of words. Some of you are saying, bring on some more eclipses. Shut this guy up, you know. But it's an amazing thing. And if people have seen totality, you agree with me? It's a truly amazing thing. You've got to really experience it to get it. I didn't get it until I went to the first one. I said, okay, now I get it. These things are amazing. People say, well, I know it's going to get dark. Yeah, but it's much, much more than that. You just can't understand until you've seen it. And then I heard something else about eclipses I didn't get until I saw my second one. You know what they tell me? And it's true. Every one is very different. If you think you've seen one eclipse, you've seen them all. No, you just seen one eclipse. So we're having another one in April of 2024 in 2 years' time. I hope to have an event. It's not too far from the Creation Museum. So I hope to have an event, maybe rent out a fairgrounds or something that day and have thousands of people there. Y'all want to come visit the Creation Museum and the Ark Encounter and do the total solar eclipse? Can you charter a plane and bring everybody with you? That would be great. I'd love to have a large Norwegian contingent. Andy, are you going to come too? All right, very good. I think it's April, can't remember the date. Is it 16th or somewhere around there of 2024? If anybody wants to look it out and shout it out for me, that'd be great. But it's just 2 years away, folks. Time's closing in on us. Here's another photograph that was taken by one of my friends in the book that we have. And then I took, yeah, that's fine. That shows the corona. The last photograph I showed just showed the inner part of the corona and some prominences. Let me go back to that last photograph for a minute. You'll see some little red things around the edge. Those are prominences. They look like little loops that stick up on the edge. If you take a short exposure, you see those, but you don't see the corona so well. If you take a longer exposure, like this next one, you don't get the prominences, but you get the corona. The corona is the outer layer of the sun. Isn't that pretty? Well, the thing is, the eye is a much better instrument than the photograph, because the camera, because your eye sees them both at the same time. No camera can do that. That's one reason why no photograph does it justice. And then right at the end of the eclipse or beginning of the eclipse, one of the two, there's a little bit of sunlight that comes through. We call this the diamond ring effect. I took this on a 35 millimeter camera with film back in 1979 at my first eclipse. I was snapping away towards the end, hoping to catch it. Do you see the diamond ring there? And when we got done with this last eclipse, I was leading a group, as I said. We got down towards the end. Somebody was giving me a countdown, 5, 4, 3, 2, 1. And I said, okay, look away, stop looking, because it's very dangerous at that point, because your eyes are dilated because it's dim light, and suddenly a little bit of bright sunlight comes through around the edge, and it can damage your eyes. I found out that both my wife and my son looked, and they saw this. I said, are you out of your minds? But they said it was really pretty. I've never seen it. I value my eyes too much. I even didn't want to risk burning up a camera, but I decided next time I'm just going to do it. And if it burns the camera up, fine. I'm okay with that. I can replace the camera. Can't replace my eyes, but that's a truly remarkable thing. I wish I would have done it last time. Well, total solar eclipses are amazing, and more amazing than you might think. They're amazing to see, but think about this. The sun is 400 times larger than the moon. Think about that, 400 times larger than the moon. So if you wanted to make a model of the Earth and the moon and the sun, let's see if you made the moon 1 centimeter across, that means that the sun would be 4 meters across, and the Earth would be 4 centimeters across. Yeah, the sun is quite large compared to the Earth and the moon. But what's interesting is that the sun is 400 times farther away than the moon is. 400 times larger, 400 times farther away, and that means that the two subtend about the same angle in the sky, about a ½ degree. So during a total solar eclipse, the sun just barely covers, the moon just barely covers the sun up. And that has two remarkable consequences. One is that total solar eclipses are spectacular. If they were, well, first of all, if the sun were larger or closer to us, there wouldn't be any total solar eclipses. And if it were smaller or farther away, they would be over total, and they wouldn't be that spectacular either. The other thing is they're extremely rare. I once read years ago, I wish I could find it again, but on average, for any given location on Earth, it's about 4 centuries between total solar eclipses. So if you're going to see one, either you got to be very lucky, or you got to actually travel, make plans, which I've done both times. There have been a few places like the eclipse back in 2017 in southern Illinois. There's a place where the track in 2024 will actually intersect. So they'll get 2 eclipses like 7 years apart. But some places it's thousands of years because, again, it's average every 4 centuries. So very rare events. Now, that's interesting, especially when you consider if you look at the other natural satellites or moons in the solar system, none of them produce rare and or spectacular eclipses. Like Jupiter has 4 large satellites or moons and dozens of others, but they either don't produce total solar eclipses at all, or they're grossly over total. They're not that spectacular, and they occur quite frequently. It's one or the other in the solar system. Only on the Earth do you have this rare combination of rarity and spectacular beauty. And it's the only planet in the solar system where it matters, because it's the only planet in the solar system where there are living creatures like you and me to enjoy this. I think God's an artist. I said it's the most beautiful thing I've ever seen. But he's also kind, and he's given us this gift. So it baffles me when people have the opportunity to see this and they don't bother. I knew people who were just, minutes drive away from path of totality, and they decided to stay home and watch it on television. I am not kidding. It's sad, but true. I begged and pleaded with a guy in 2024 we were staying with in Oregon. I said, man, you got to go see this. No, I'll just stay here and watch it on TV. And he had no idea. Had he gone, he might have said, oh, yeah. You know who Ken Ham is? His daughter is married to Bodie Hodge, one of our employees. They have several children. And he made packed the family up and took them, a few hundred miles to get to totality that morning. And his wife didn't want to go until she got there. Her jaw fell open when she saw it, and she wouldn't shut up talking about it for a week, just raving to everybody. Just on and on and on. So it's amazing what it does to people. And again, I just think it's a fantastic gift that God has given us. Isn't he wonderful? And now, of course, you can just think this is an accident. You can think there's just a coincidence that this happened. But I ask you, how many coincidences are you allowed to have before you begin to realize maybe they aren't coincidences at all? Now, what about the moon? As it turns out, the moon is an amazing object. I've come to really appreciate the moon in the last couple of decades. I really didn't realize some things. And there's some design aspects about the moon that I didn't know for a long time. First of all, the moon is relatively large compared to the Earth. Now, what I mean by that is its mass. If you measure the mass of the Earth and the mass of the Earth has about 81 times more mass than the moon does. Now, 81 may sound like an awful lot of mass more than the Earth has than the moon. It's kind of lopsided, isn't it? But when you look at the other planets of the solar system, the closest anyone comes, one of the satellites of Saturn, Saturn is 4,000 times more massive. 81 is not very large at all, is it? And the others are tens of thousands or hundreds of thousands to one. So when you do the comparison between all the satellites and their planets in the solar system, you'll find that the Earth and the moon are relatively close in mass, more so than any of the others. But the moon also has a unique orbit around the Earth. Now, you all know that we go around the sun once a year, right? I hope you all know that, given my talk last night particularly. All right, so you're going around the Earth like this. Now, the path we follow around the sun is called the ecliptic. E-C-L-I-P-T-I-C, ecliptic. That's the plane of the Earth's orbit. Now you know that the Earth's rotation axis is tilted like this by 23.5 degrees. We astronomers have a really fancy term for that tilt. You know what we call it? the obliquity of the ecliptic. I think tilt's easier to say, isn't it? All right. So you got that tilt of 23.4 degrees, and the equator is halfway between the two poles. So the equator on the Earth is tilted, its plane of the equator is tilted 23.4 degrees to the ecliptic, plane of the ecliptic. And of course that tilt is what gives you the seasons. I've noticed you only get about 5.5 hours of no sunlight right now, and I went out close to midnight last night, and I was having a hard time finding any stars at all because it's just twilight. It's not dark out there at all around midnight because how far north you are. Where I live, it gets dark for about 6 hours a night right now, totally dark. So it's really, if you're living out in the country someplace particularly. All right. Turns out many of the larger natural satellites or moons in the solar system, they orbit in the equatorial plane. That is above the equator. Jupiter's four large satellites, they move up in the equator. Saturn the same way. Other satellites, smaller ones, they have weird orbits going in weird directions. The moon, however, doesn't orbit in the equatorial plane. It orbits in the ecliptic plane, the same plane that we follow around the sun. Now, there are about 200 known satellites or moons of the planets in the solar system, most of them very small. You know how many of them orbit in the ecliptic plane? Only one, the moon. That's it. That's weird. It actually tells you several things. One thing it tells you is that the origin of the moon is unique. Well, duh, the Earth is unique. Why would its moon be? Why would the moon not be unique as well? But there's something else going on. It stabilizes the the Earth's orbit on its axis. Stabilizes the Earth's tilt on its axis. You see, that tilt doesn't remain fixed. You may have grown up hearing it was 23.5 degrees. How many people remember that? 23.5 degrees? It used to be like 23.47 degrees. Now it's 23.44 degrees. It changes. Why? Well, because there are forces out there in the solar system. The sun grabs hold of the Earth's tilt. Jupiter and other planets grab hold of the Earth, and they want to move that tilt around like this. They produce a torque on the Earth, which will do that. And if left unconstrained, those forces would slowly but gradually over time, they would take the tilt to 90 degrees, and they'd take the tilt back to 0 degrees. And it would waffle back and forth, kind of erratically as it does that, between 0 and 90. What would that do to the Earth? Oh, it'd be horrible, wouldn't it? Yeah, you don't live too far from the Arctic here, do you? A few hundred kilometers, I guess. But if you made the tilt like go 30 degrees, you'd be in the Arctic. If you made the tilt 60 degrees, you'd still be in the Arctic, but you'd also be in the tropics. What do you think that would do to living things like plants? It would wreak havoc on it, wouldn't it? It would be bad. So the moon, its presence stabilizes that tilt till it only changes through a range of about 2 degrees. It can't go outside of that range, which I think we can handle a 2-degree change. Now, why does it do that? Well, because of 2 factors. The moon's relatively large mass compared to the Earth. If it were not really massive at all, like most satellites of the solar system, it wouldn't do it. And its unique orbit being in the ecliptic plane rather than any other plane. Now, you might say, well, that's just an amazing coincidence. You see, it's the only planet in the solar system where it matters because it's the only planet in the solar system where there's living things. But again, I ask you, how many coincidences are you allowed to have before you begin to realize these are not coincidences at all? And I'm also of the opinion that the moon made physics possible. Now, it doesn't mean that physics was created by the moon. What I mean by that, the moon made it possible for man to figure out physics. Does anyone know who wrote the founding document of physics as we know it? Anybody know? Who wrote the book that, literally wrote the book that defined physics for us? Anybody? Not me, no. It goes back about 350 years. Got an Englishman here, and he isn't even raising his hand. Anybody? Yes. Sir Isaac Newton. Ding, ding, ding. You win. Everybody was thinking that, but no one wanted to say it. Thank you for saying it. Sir Isaac Newton. The man was truly brilliant. By the time he was 23 years old, he had invented physics, he had invented calculus, he had invented a whole bunch of stuff before he was 23 years old. How many of you at least 23 years old here? What have you done lately? He just did that in his spare time. The man was incredible. Probably a mind like his comes along once a millennium. And turns out I think he knew that. Interesting man, by the way. Very interesting man. He was probably on the spectrum somewhere. You know what I mean by the spectrum? I'm on the spectrum. I have CDO. You know what CDO is? Obsessive compulsive disorder. Go ahead and ask me. CDO, obsessive compulsive disorder. Go ahead and ask me. Come on.
Obsessed with stars?
Pardon?
Obsessed with stars?
No? Well, some people want to call it OCD, but they don't care to alphabetize it, see? So, well, then you have also have Tourette syndrome, you have Asperger's, all those other things. They're on the spectrum, and it turns out I think Newton was on the spectrum. Almost everybody agrees now he's on the spectrum somewhere. We don't know, but he had some funny quirks. You probably didn't notice my CDO. If you pay attention, you'll notice I have CDO. All right, but a brilliant man. But he wrote this book. Anybody know what it's called? The founding document of physics and so forth. It was called yes, Andy. Given the whole thing, Principia. It was written in Latin. It's Principles of Mathematics and Natural Philosophy, is how it translates, which is science, translated into English. Really incredible book. But you know what his big triumph in there? He had his 3 laws of motion. Remember those from school? And he had his law of gravity, and he put all of those together. But question is, where did he get his law of gravity? This is something I used to teach my physics students. I thought it was marvelous, and the students were not terribly impressed, which means they weren't paying attention or they didn't get it, as I often say. But I'll try to share it with you, the enthusiasm I have for this man and what he did. The big question was, he realized that applying his first law of motion, that if there's no force acting on the moon, it's not going to go around the Earth like this. Going around the Earth requires there be a force pulling it all the time, the centripetal force, we call it, making that happen. And his great insight, his great leap, was to understand that the force that caused the fig to fall off the tree and hit him on the head, it was a fig, not an apple. Think about it. Fig falls off the tree and hits him in the head, hit Newton on the head, and he realized, or took as a hypothesis, that the same force that made that happen was the same force that caused the moon to orbit around the Earth. That was a tremendous insight, and this is how he did it. He knew that the moon was 60 times farther away than we were at standing on the surface of the Earth. That is, the moon is 60 times farther from the center of the Earth than we are when we're on the Earth. What I mean by that is the moon's distance from the Earth is 60 Earth radii. Okay? So we're 60 times closer to the center of the Earth. That's the center-to-center distance. That's important. Everybody understand that? 60. Sometimes people ask me, well, how did he know how far away the moon was, and how would he know the size of the Earth? Well, last night I dealt with that, right? A guy named Eratosthenes, nearly 2,000 years before Newton, measured the size of the Earth, and it turns out, not long after that, by around the 1st or 2nd century AD, people had measured the distance to the moon pretty accurately. They knew it was 60 radii back 2,000 years ago. So it was ancient knowledge at that point. Now, on the Earth, you can measure the acceleration of gravity. I have my physics students do that quite frequently. People had measured it. It's 9.8 meters per second squared. But Newton was able to take his laws of motion and work out a relationship for centripetal acceleration. And he was able to measure, or actually compute, from the distance of the moon from the Earth and its orbital period, which had been known since ancient times, what its acceleration required to keep it in orbit. And what he found was the acceleration we experience on the Earth's surface was 3,600 times more than the acceleration required to keep the moon in orbit around the Earth. Now look at those two numbers, 60 and 3,600. Anybody know the relationship between those two? What's that? Yeah, you take 60 and you square it and you get 3,600, don't you? If you've studied Newton's law of gravity, you will know it's called an inverse square law, because 60 squared is 3,600. Newton had this relationship worked out where the attraction of gravity is inversely proportional to the square of the distance. And if there was no moon orbiting the Earth, he would have not had a problem to solve, and he would have never gotten this law of gravity. Are you impressed? Oh, yeah. If I lived to be 300 years old, I would have never seen that. But Newton did it before he was 22 or so. You know, he was a young, smart guy. All right? Now, once you do that, he writes his Principia, has his three laws of motion, and when I taught physics for many years at the university, the first semester, much of what I did that first semester was what's called mechanics, Newtonian mechanics. We later on got to some other things like heat and electricity and magnetism, but the first thing in any physics class, physics class, is mechanics. You do the laws of motion, you do accelerations, forces, all of those sorts of things. That's right out of Newton's Principia. Physics has not changed that much in 3.5 centuries. Goes back to Newton. If there weren't a moon orbiting the Earth, though, we would have never had that. So God gave us the moon and he gave us Newton. And together, that produced physics for us. As I said, I'm always impressed. Newton is one of the most impressive men I've ever seen. You know, in recent times we talk about how bright people are, like Albert Einstein or Stephen Hawking. They're pikers compared to Newton. Newton runs circles around all of them. He was the most impressive mind I have ever seen in the history of science. There are some other good ones out there, but he was the best by far. All right, what about the Earth? The Earth here taken from space. Not sure which spacecraft took that one off the top of my head here. But there's some unique things about the Earth that are amazing. For instance, we have this proper distance from the sun. You know, astronomers define what's called the what's the term for it now? The habitable zone. You take the brightness of a temperature and brightness of a star, and you can calculate a distance that a planet must orbit that if it has the right kind of atmosphere, that you can have liquid water. If a planet obviously is too close to the sun, liquid water can't exist. It's going to be too hot. If it's too far from the sun, it can't exist. It's going to be too cold. It's going to be frozen into ice, or it's going to be in a gaseous form. So it's a very narrow range. We call it the habitable zone. Sometimes we call it the Goldilocks zone. Do you know the name Goldilocks and the Three Bears? Right, so we have Goldilocks zone because it's a perfect place for a planet. Not too hot, not too cold. It's just right. Well, guess where the Earth is? It's in that Goldilocks zone. Just a coincidence, you say. Well, you know, being the right distance from the sun is a start, but it's not a finish, because you see the moon is in the Goldilocks zone too. It's co-orbiting with the Earth, yet it's dead as can be. There's no life there. Why not? Well, you have to have a couple other things going on for you. You have to have the proper size. You see, the problem with the moon is that it's too small, the gravity is too small, and the surface of the moon is about 1/6 the acceleration of gravity we have on the Earth. Consequently, it can't hold on to gases. Did you hear about the first restaurant on the moon? The food's out of this world. But there's no atmosphere. Well, that bombed. Maybe it doesn't translate well into Norwegian. It does? They just didn't think it was funny, huh? Okay. But the moon has no atmosphere, and would you agree it would be kind of hard to live without atmosphere? Oh, yeah. For one thing, you had to hold your breath all the time. The other thing is the fact that if you don't have atmosphere, you can't have the pressure to hold on to water. And by the way, I kind of skipped over this fine point, but would you agree that liquid water is essential for life? Yeah, I could give a whole talk just on the neat properties of water. But we're made of like 70, 80, 75% water, and water is a universal solvent. It's inconceivable that life could exist without water, liquid water. And in fact, when people go looking for life elsewhere in the universe, they're looking for places where liquid water might exist. That's that important. They learn that lesson from the Earth. It's also important that you have a nitrogen-based diatomic atmosphere. 78% of what you breathe in is nitrogen. Diatomic means 2 atoms per molecule. So you breathe in, you get about 21% oxygen, about 1% everything else. What's the 78% doing for you? Is nitrogen? Doing absolutely nothing. It's just taking up space and providing bulk. If you had say a 50% oxygen environment, would that be good? Turns out it's not. 100% is really bad. You've heard of the Apollo 1 fire in 1967? That's because they were running 100% oxygen. A tiny spark, and it went up in flames in a hurry, and it killed those astronauts with smoke inhalation in a matter of seconds. It was that bad. You don't want a high oxygen content. 21% is pretty much ideal. Isn't that an amazing coincidence that happened? But nitrogen's very important. They're now looking for life on other planets, around other stars, and you know what they look for? They look for the James Webb Telescope will help them do this, by the way. One of the things it has is to try to get some spectroscopic information on some of these planets orbiting other stars. And you know what they're going to look for? Nitrogen-based atmosphere, diatomic nitrogen-based. Where did they get that idea? Well, from the Earth, of course. Now, again, you can say that's a coincidence. You need liquid water. Again, that's a coincidence. And we can look at the atmospheres of other planets. I have there the Earth, and to the left of the Earth is Venus, to the right of the Earth is Mars, and let's see, to the right of Mars is one of the largest asteroid. To the left of Venus is one of the satellites or moons of Jupiter, and to the upper right of the Earth is Moon. Those are all to scale, by the way. And you look at these bodies, and none of them really have liquid water at all. Now, we have a poem in English literature, The Rime of the Ancient Mariner. Anybody ever read that story? And there's a classic line in there. It's about a sailor who is adrift at sea, and he doesn't have any drinking water. And the irony is he's surrounded by all this water, but it's salt water. And so he laments, water, water everywhere, but not a drop to drink. And as it turns out, water is pretty common in the universe. Well, I should say H2O is common in the universe. But everywhere we see it, it's in either a solid form or in a gaseous form. We've never actually detected liquid water anywhere else in the universe. Now, we have some hints that there's some liquid water out there, but we've never actually directly observed it. So it's amazing. Not on the Moon, not on Venus, not on Mars, and not on the satellites of the planets. Again, a lot of those objects I just shared with you have some water there, but they're H2O. It's a gas or it's solid. Now, look to Venus, it's too hot. Look to Mars, it's too cold. Some people ask me sometimes, why did God make the other planets? And I know little pieces and bits of this here and there. One thing I think about Mars and Venus is that they're just inside and outside the habitable zone around the Earth, sun. And it shows us, I think, just how wrong a planet can be. Because you know what? Venus is almost identical to the Earth. Its mass, its size, its density, everything is like the Earth except for one thing. It's nothing like the Earth when you look at the conditions on it. It's the hottest surface of any planet because of a huge greenhouse effect that takes place because it has a very dense, thick atmosphere. Another thing that's interesting, this is another talk I could give. I'm not giving this time. But did you know that there was once, secular scientists think this isn't creationists, they think there was once a global or near global flood on Mars? Yeah. On a planet where there's no liquid water today? But a flood couldn't happen on Earth where they have all this water. It's amazing, hardest of hearts. And by the way, we think there's a lot of tectonic upheaval that took place during the time of the flood. Venus was completely reworked not too long ago. That's like 150 million years ago, which is not too long ago according to evolutionists. And the entire surface was overturned in less than 1 million years. Very fast. That couldn't happen on Earth, though. It's amazing. They have evidence right there on one planet and the other planet of this catastrophic stuff taking place, and they deny it could have taken place on the Earth. Am I running out of time? Oh, okay. I'll wrap it up real quick then. I'll very quickly go this. I'm running out of time. I'll have one major point. I'm going to skip over some of the details. I want to mention the fact that we've discovered many planets around other stars. We call these exoplanets. And this is one way we do it. It's a similar kind of work I do. I do stars that do this, but this is a star and a planet. Suppose you have a star and there's a little planet passing in front of it once each orbit. The light that you observe, the light curve across the bottom there, when it's out of eclipse or out of transit, we would say, it's not passing in front of it, it's going to have constant light. But when the planet passes in front of the star, it's going to block out light, and you see that little dip. That's theoretically what it looks like. That's actual data down below there, showing you the dip that takes place. We've discovered thousands of planets this way around other stars. The count now is more than 5,000 exoplanets. Why are we looking for planets around other stars? Number one, to prove that planets are common. Number two, prove that solar systems, that is multiple planets around stars, are common. Number three, to prove that Earth-like planets are common. And number four, prove that life is common in the universe. They're looking for Earth-like planets. What have we found? Number one, planets are common. With 5,000 planets? Yeah, they're pretty common. We found several stars that have multiple planets, so it turns out that solar systems may be common. We don't have enough data yet, but it looks like it's probably that way. But what about Earth-like planets? Turns out they're not common. Out of the 5,000 planets we've found so far, how many of them are Earth-like? 0. None. It's amazing. Occasionally I'll hear news of a Earth-like planet discovered, but usually it takes me only a matter of minutes to look on the internet and give you 2 or 3 reasons why it's not. It's not that hard. It really isn't. It's wishful thinking that they have. So when a new Earth-like planet's discovered, I very quickly go out there, do a study, and then I will publish on our website, answersingenesis.org, why it's not an Earth-like planet. There are none at all. And so consequently, there are no habitable planets yet. I think the solar system and the Earth are unique in the universe. I think the science, with 5,000 exoplanets, we can call it, we are alone in the universe. You've probably never heard a scientist say that, but I think the data really support it. 5,000 data points? Come on, I've seen papers published with only 5 data points. We got 5,000. Let's call it, folks. Well, why don't they call it? Well, because this is the one issue in science that's way beyond science. Because you see, if we are alone in the universe, that suggests that maybe we're unique, and in which case there must be a creator. And if there's a creator, then we're beholden to him. We have responsibility and accountability to him. And man, its hardened heart can't do that. How hardened are their hearts? I will close with this. Back in the 80s, there were 2 people, Barrow and Tipler, who wrote a book called The Anthropic Principle. What is the Anthropic Principle? It was coined in 1972 or 73 by Brandon Carter. It's a number of coincidences that seem to make the universe suited for humanity's existence. The widest form is just the universe as a whole, but we can talk about just planets if we wish. Barrow and Tipler, back in the 80s, wrote an extensive book, over 1,000 pages long, where they give the history of the Anthropic Principle, different versions of it. They consider all the evidence about the Anthropic Principle. Remember what it is. It's the number of coincidences that seem to make the universe suited for humanity's existence. And their conclusion was that it only appears that way. I am not joking. They said it only, the universe certainly looks designed to us, but it isn't designed. Remember when I opened up, I said design is not a conclusive argument. If you believe there's a God, you're going to see it. But if you really don't want there to be a God, you're going to tend to ignore it. That's exactly what they're doing here. And that's the reason why they keep looking for exoplanets, and they refuse to make that conclusion that's legitimate according to our evidence we have. Thank you very much. I apologize for getting into lunch.